All right, welcome back to Bill Westlake Programming. In our last lesson, we talked about streams and header files and a little bit about references. We talked a little bit about defines and how you can move some things around. That was just kind of an overview. In this lesson, I'm going to get rid of some of this stuff. In fact, I'm going to get rid of all of this stuff. In this lesson, we're going to talk about three very fundamental concepts in C++. They are values, references, and pointers. And we're going to look at each one of those in some detail, but we're going to get more involved in them later and what you can do with them. Let's begin with values. What exactly are values? Well, a value is just a number or a character string or whatever it may be. If we say int a equals 3, 3 is a value. A is now a variable. It's a named location that holds the value 3. I'm going to create a quick function, and we're going to talk more about functions as we go along. All right, so this simple function what? Oh, expected semicolon. All right. Oh, expected a semicolon here. What's wrong with me? Okay. All right. It's late. We make mistakes typing all the time. Just I work in multiple languages and things happen. All right. This function that I just defined is very simple. This says it returns an integer, and its name is add, and it takes two values as parameters, an integer called a and an integer called b, and the result that it returns is simply a plus b. This function is expecting two values for a and b, and it can be called in several different ways. Let's get rid of this for the moment, and let's say int c equals add 3, 4. And just for convenience, we'll do our standard : C out from C from the answer is C from standard : and del. All right. If we run this, what'll happen is it will call this function add 3, 4, take the result and assign it to C. Then it'll run this and it'll print out C. So let's run it and just make sure it works. And there, the answer is 7. And that is, of course, 3 plus 4. So what's happening here? What we're doing is we're passing values into this. And the value 3 that's here gets passed in, and a copy is placed in A. It could be in a register, or it could be passed in on the stack, or whatever the compiler thinks is important. It's going to pass it into these as a value. A literal 3 is going to be put into this function. If you have a more complex thing, like a bunch of data in a structure, and you do the same thing and you just have the structure here, it's going to do exactly the same thing. It's going to make a copy of it and pass the copy in. And that, for small structures even, can be a good thing to do. There are many reasons why you might want to just have a copy of a simple structure with a few numbers or something and it be copied in. But this kind of construct is always going to take a value and it's going to pass that value in. Let's do something slightly different. let's say int add ref int ampersand a int ampersand b. And we'll turn a plus b. Now, if I do add ref with 3 and 4, there's going to be a problem. We can't send these literal values 3 and 4 into this function. Why? Because they're values, and this expects references. So this is how we can do it with a reference. We'll say int a equals 3, int b equals 4. And by the way, you'll see some situations with multiple assignment lists and stuff. I'm not real fond of them, and I'll explain later. But if we just send in a and b now it can accept them, because these have a memory location, and what it's passing in is a reference to a. It's a non-constant reference. So we can do something very, very funny here, and I'll get to that in a moment. Right now, we're just going to run this, and we'll see that we get exactly the same number as before. When we run it, it's a 7 right there. And I'm sorry, I hope this is visible. It's kind of small, even on my screen. I guess I can change the font on this and make it a little bit bigger. Let's pump it up to here. Hopefully that's a little easier for you to read on the video. But yeah, the answer is 7. All right, what's going on here? Inside my main function, this int a equals 3 and int b equals 4 has created some kind of memory location. It might be on my local stack, or it might be in some data areas within my main function. That's all up to the compiler exactly where it's stored. But a, being a variable, has an address in memory, a place where it is stored. Because this add reference is expecting a reference, and that's what this ampersand means after the int. It means I don't want a value, I want a reference. I want a memory location of where I can find my number. And a plus b is going to translate those into machine instructions that tell it to look up that address and get that value from the address specified here. And it's going to use those to return the value. And what it's returning in this case is a value. And we don't want to get into returning references right at the moment. We will get to that in a moment, though. We'll also do one where we return a reference. Although we don't have to actually return it. And I'm going to show you why right now. This function can do something very funky and very bad. These are non-constant references. And what that means is that this function can modify the value stored in a at this address down here. So let's do that. Let's modify it. Let's say a equals 4 right here. And instead of just printing out C, I'm going to print out the answer a a b equals quote C. So this is going to I need one of these here, and I need one here. Okay, what this is going to print out is the value stored in this a plus a plus sign, the value stored in this b equals the answer C. Now I've said a equals 3, and I'm calling add ref ab, but my function up here is saying a equals 4. Let's run it. And it says now 4 plus 4 equals 8. Okay. what's happening. Because we passed a reference into this and it's not a constant reference, this function can modify what's at that address down here. So this function up here that I called here is reaching back into my main function and it's altering this value. This is not a good practice in most cases. There are some specific reasons why we might do it, why we might let this modify something, but we would have a reason for doing it and we probably wouldn't be trying to send a value in. This code at this point is very confusing. We say a equals 3, b equals 4, add ref a, b, and we get 4 plus 4 because this is setting this. However, if we come up here and we put the constant keyword in here, this no longer compiles. And I'll show you that. So we get an error now. And a, you cannot assign to the variable a. This, by saying constant here, is now illegal. We've just restricted this function can no longer modify these values down here. They're still sending a reference. It's still sending an address. And it can use the address. It can get it and add it together and return the value, but it can't modify it. And if we run it now, of course, we will get the answer that we would expect. 3 plus 4 equals 7. So that's a little bit about how references work. Now I'm going to go over the one case where you might want to do a modification. And we'll still just work with integers, but really this would probably be something you would do with a struct. And it was done extensively in the old C days where everything was C. We did this a lot, but I'm going to do something here where I'm going to return a reference to an integer, and I'm going to call this add ref 2, and I'm going to send in a constant int a, int ampersand a. I'm going to send in a constant int ampersand b, and I'm going to send a int ampersand, and I'm going to call it result. Now what I'm going to do, you know what, I'm not going to return this. I'm going to make this a void function. This isn't going to return a value. What it's going to do is it's going to add a and b together, and it's going to assign it to result. So now we can say result equals a plus b. And now instead of saying c equals add ref, we're going to get rid of this, and we're going to say this add ref 2, and I'm going to come here and I'm going to say int c equals 0. I'm going to initialize it to 0, and I'm going to pass c in there. Oops, that's supposed to be a comma. All right, so now what's happening? When we call add ref 2, we're going to pass it a constant a and a constant reference b. Okay, this function can't modify these two, but it can modify this one. We're giving it permission to. We didn't put constant here, and it's not going to return anything. It's just going to assign to this result the sum of a and b. And now c is a reference here that's going to get modified by this function on purpose. We've told it to. Now, in this particular case, this probably isn't a good idea, but this particular pattern has its uses and reasons why we might pass something in and ask it to modify it in some way, or fill it in with some data and bring it and let us just carry on with it. And so now if we run it, we get the same answer. We get 3 plus 4 equals 7. You'll notice that c is this c here, and we set it equal to 0, but this add ref 2 set it equal to the sum of a and b, and it changed it in place here. And that's the difference between a value, a reference, and a constant reference. Keep those in mind. All right, let me double check the time here. What are we looking at? 14 minutes, we're okay. So now we're going to talk a little bit about pointers. Everybody seems to get a little bit lost with pointers. So I'm going to try to see if I can explain these very carefully. I am going to just go ahead and delete all this code. We don't need it any further. I will leave it up on the screen in case you want to copy it. You can pause here. It's all together on the screen. That'll be harder to do later when we get longer. And I may post this up, all this code up on GitHub at some point so you can see it. In fact, no, I won't delete it. I'll leave it in the file. We didn't really need that early stuff, but I'll leave it in the file. Let's do one more. Let's do this same exact thing here, but let's do it with pointers. And so I'm going to get rid of the constant here, and I'm going to make this an int pointer A, an int pointer B, and I'll make this an int pointer result. Now, this doesn't work anymore. It doesn't understand what we're adding together. In fact, we would be adding addresses together. So we can't do this exactly the same way. Why not? Unlike a reference is in fact a pointer. Like I said, it's an address, but it's a special kind of pointer that says, don't treat this as an address. Treat this as a value at the address. And we call that dereferencing. A reference is automatically dereferenced for us, which is why we can just use A here plus B, because these are references. The system will automatically dereference this, get the information at the address, and let us work on that, the actual address of it, the data that's stored in it. Pointers are looser than references. When we pass a pointer to an int into this function, the function is receiving the address. It's not dereferenced. And we'll see the importance of that shortly and the usefulness of it. But now what we have to do is say that, in fact, we can't, well, we can do this. We can dereference. We can say pointer result equals pointer A plus pointer B. Well, okay. What does this crazy mess do? It does exactly what this one does. Remember I said this was automatically dereferenced? Well, down here we have pointers, and we have to manually dereference them. This pointer at the beginning, or this star, this asterisk at the beginning of these variables says, I don't want to deal with the pointer, which is what this is. It's an address. I want to deal with the data at that address. And I want to deal with the data at this address, and I want to deal with the data at this address. All right? If we change this to, it's already addref. Oh, we copied that. This has to be addref, not addref. This has to be add pointer. And if we change this to add pointer, now we will also have an error. All right, now this IntelliSense is telling me the errors before I ever compile it, which is really nice. Feature of Visual Studio. I'll talk more about that. What's this saying? Well, it's saying you're trying to pass a reference into a pointer, and you need to pass a pointer. And how do we do that? Well, we have to give it the address of A, the address of B, and the address of C. And we do that with an ampersand. But unlike the ampersand up here, which is in a type, this is going to be an ampersand associated with a variable, and we put it before the variable, like this. And this particular ampersand, unlike this reference ampersand up here, says, no, don't send 3 into the function. Don't send the A value, the reference to 3, or the reference to A in. It says send the address or the pointer to A. So now we're literally sending the address of A, the address of B, and the address of C into this function, which accepts a pointer to int, a pointer to int again, and a pointer to int here as the result. And this is dereferencing the result from the pointer to the value and assigning that value pointed to by this address to the sum of the two values pointed to by these two addresses. I hope you followed that, and I'll try to maybe explain it a little differently again, but let's run this program again and see what happens. And we still get 3 plus 4 equals 7. So just like the reference one, this dereferenced B, dereferenced A, got those values out of those memory locations and assigned the result to this C variable down here via its address here. And that's the basics of that kind of pointer. There's one other way of looking at pointers. Here we're looking at the address of an integer. There's another kind of pointer that can be also treated as an array of elements. And it works exactly the same way. In fact, this int pointer A is treated as an array of values. So we can modify this slightly. Let's do this. Let's add another integer value at the beginning called len. All right. And I'm going to make this 3. And now I'm going to get rid of these. And I'm going to create an int pointer vals equals new int 3. And I will explain what this does. And I'm going to say 3, 4, 0. All right. So, actually, I didn't want to do this. I want to copy this function again. Add array int len, comma, and we need to get rid of this. And we can get rid of this for the moment. All right. What are we getting in here? Int vals, and this is going to make, and we're going to go int ampersand result. All right. Constant, and no, it can't be a constant. All right. What do we want to do here? Well, this pointer, even these are actually arrays. But we set it up as a single element array is what we did. And we don't have A and B down here. We'll fix that in a moment. Now we've got this int pointer vals. We can treat this as an array of this len. Doing it this way, you have to coordinate this. You have to make sure you send the right length in. This is short for length, and you got to send the correct length of this in. Otherwise, you could have a buffer overflow issue. And I'll show you how this works. What we're going to do is very simply, we're going to make a for statement. Int I equals 0. I is less than len I plus plus. And I will explain in a moment how that for statement works. This is your first introduction to the for statement. So now what I want to do is I want to have a integer called result. And I'm going to initialize it to 0. And I'm going to say that result plus equals. Plus equals just means add and assign. And what are we going to add? Vals sub I. And then we're going to say, I want to call this result. Call this, we'll call this up here return val. We'll call that result. Result plus equals vals, and then we'll just say ret val equals result, and that's legit. So we've got that, that, and that. Now we can no longer do this way. We now have what I've created is an integer pointer, which is actually an array of integers. Now, I could have said 3 here. I could have put this as, but I wanted to highlight that this is also a pointer. That this array construct here is equivalent to this, but this allows me to specify a size for this new operator, which is going to allocate the memory on the heap. There's something else we need to do before we return, and that is we need to delete vals. And we use the delete array because we created an array up here, and so we want to delete this array of vals, or we would have a potential memory leak. And now all we need to do, we know it's a 3. In fact, let's do this. Yeah, we know the length is 3, and our numbers are 3, 4. Let's make it 3, 4, 5. We need a result, and we'll just call it result. And so we want to call that add array. We want to send in a length of 3. We want to send in our vals, and we want to send in our return value, which is result. Okay, and that part should work. Now let's run our for loop again here. Int I equals 0. I is less than, we'll just say 3. I plus plus. Before we do that, we'll go standard colon C out from results. So we'll start by printing out our little array, and what we'll do is we'll send out vals sub I from plus quote space plus space. You got to put a semicolon up here. Semicolon. Except if vals is less than 2. If vals is less than 2, we'll do that. 0, 1, 2. Else if I is less than 2, colon C out from val sub I. Don't pay too much attention to my typing. I go back and forth and type all over the place when I'm coding. I'm not the neatest, especially when I'm kind of coding out of my head like this. Then we want to go C out, or standard colon C out from equals from, and it's our result from standard colon endel. And I think this should work. So what's it going to do? It's going to take this array of numbers we created here. It's going to pass it into this function along with the length and our result that we're going to get back. This function's going to run through all those vowels, add them up, and return the result. And then we're going to sort of try to print out a semi-formatted look at this. 0 and 1, and when we get to 2, we don't want the plus after it. So we still want vals sub I. See out from vals sub I down here. The only difference is that we don't want the plus, we want the equals. So this should print out all our numbers. Let's see what happens. 3 plus 4 plus 5 equals 12. And it does. 3 plus 4 plus 5 does in fact equal 12. So what happened was it took this array of numbers, passed it into this pointer value here, which can be treated as an array. And the nice thing is we can access it with this construct here as an array. We could also do pointer arithmetic on it. In fact, I'll show you exactly how that happens. We'll just go vals plus I, and we'll dereference it. Let me run it first. 3 plus 4 plus 5 equals 12. So what's this saying? Well, remember, vals is an address. It's an address of the beginning of this block of data. And it knows that the block of data is integers, which could be, depending on the system they're running on, they could be 2 bytes or 4 bytes or even 8 bytes, depending on what kind of system they're running on. The system knows when I take that address and add a number to it, it knows that I want to increment by the length of this integer type within the system that I'm on. So it's going to increment this. In the case of integers on this system, they're going to be 4-byte integers. So it's going to increment at 4 bytes every time. In fact, we could go in here and do a little standard colon C out from address from vals plus I from and L standard. And before while it's actually doing the calculations, those will run out. So we're going from an address of 9A, 99, 9A, 9B, 9C. That's 4. And then from 9C, we're going to 9D, 9E, 9F, A00. That's 4 bytes. So an int on this is, in fact, 4 bytes. And even though I'm adding I to it, the actual address is incrementing by 4, which is the size of that integer. So that's kind of the magic of pointers. We're going to get more into pointers to objects, pointers to structs, pointers to all kinds of things. Pointers are extremely useful, extremely valuable. You can make arrays out of them. You can do all kinds of things with pointers. And in the standard library, there's also the idea of a smart pointer, which turns pointers into very special kinds of automatically handled lifetimes and stuff. We'll get into all of that at a later date. But that's it for this video. Thanks for watching. I hope you enjoyed it. If you enjoyed the video, hit that like button. If you really liked it, hit that subscribe button. And if you want to get notifications when I upload videos, hit that notify button. Thanks, and I'll see you in the next video.